We're going to look at the review that I gave you guys yesterday. Okay, we're going to start on the front page. Number 1 is going to work our way to the back. Okay, so the first problem was really just basically going way back, talking about normal distributions. Can you take the mean and standard deviation, label the curve, and basically going with letter B, let's shade our area that we're looking to find the probability of. Now this one didn't ask me to use a sample size. It's just a single sample, single individual. So we use the standard deviation they gave us in the problem, and so that's why you get your values of 90 on the bottom, and 100, 110, 120, and so forth, going up and down. So you can see those right here. Going back below, we subtract 10, go each time. Now going on to question part B, it wanted to know what's the probability that x is greater than 100. Well, there's really two ways to do it. The first way is kind of straightforward, the 68, 95, 98.7, using the empirical rule. Basically, if we were to add up the areas, because that falls on one of our whole standard deviations, I can take that and add up the 13.5, the 2.35, and the 0.15, and I get this over here. Now, we know a little bit more accurate way to do this because we've been able to look at the z-scores, been looking at the z-table, as well as using the calculator to provide that normal distribution probability. So if we use our calculators, we use normal CDF. We're going to go ahead and we're going to use our 100 up to positive infinity. We use our mean of 90 because in this situation we've taken a sample size of 16, but remember, central limit theorem says that it doesn't change the mean, so it stays the same. And here, we're still at one sample of 1, so we're still going to use the sample that they originally gave us. And so that's where you have 10, and you notice that my exact value is really close to 16, and so we have 0.1578 or 87. So just under 16%. In part B, this is where they tell us to take a sample of 16. We go ahead and recalculate that. This one talks about a different scenario. We're looking at between 93 and 96. And so you've got a situation, this is my lower limit, this is my upper limit. In this problem, we're going to have to change, well, of course we'll change the beginning and ending points, but we're also going to have to change our standard deviation. Since we took a sample of 16, we're going to take the original standard deviation they gave us, divide that by the square root of the sample size, just like we've always done, and that's going to give us a 2.5 standard deviation for a sample of 16. Now, you can see this one's the probability has dropped a little bit, so it's just slightly under 11%, so 0.1069. This, we did discuss this a little bit. Let's just find the median to average speeds. There's a couple of ways to do this, kind of easy both ways, but the mean and the median for any symmetric distribution is the same, period. Now, if you don't remember this, remember that anytime I'm looking for x values, anytime I'm looking for numbers, then I'm going to be using inverse norm. When I'm looking for normal CDF, that's looking for probabilities. So we're going to say, well, I know that the median represents the 50% mark, so we're going to put that in for 0.5. We're going to put 90 as my mean and 2.5 as my standard deviation. It turns out, just like we thought it would, gives us 90. And interestingly enough, if you type anything in the standard deviation, it doesn't matter. You could type in any number you want. Because we're looking at 0.5, the mean is going to be exactly the same as the standard deviation, as the median. So this has no effect technically because we're using a 0.5 as my probability. And that's number 1. Okay. If you need to go back and pause this, so most of this stuff is pretty straightforward, but if you need to pause this or rewind it if somebody misses something, please feel free to do that. Alright, number 2. So for number 2, it changes a little bit, gives us a different scenario. Looking at an apartment, the mean of the apartment says 1800. You have a standard deviation of 150. The sample size is 25. The first part says sketch a graph and label the horizontal axis. Notice this gave us the sample size in the original problem, so we're going to have to make sure to edit that and create the correct standard deviation before we fill out our curve at the bottom. So in this case, you can see us. We have a mean of 1800, and it goes to 1830, 1860. It's going up by 30, and then of course going down by 30 as well. Now, if you look at part B, I put an asterisk here because we really didn't talk about the PDF. We didn't really use that a whole lot, and I'm not going to give you that. And so the only reason I used PDF here is because it didn't give me a range of values. It didn't say more than or less than. It said, what is the probability that the cost would be exactly $17.90? So that's a specific value. We didn't really talk about that. So you use the PDF to find that out. You type in the number you want, the mean, and the standard deviation, kind of what you see here. But don't worry too much about that. Part C. This is kind of traditional. We said find the probability that x is greater than 1750. We plug in our values. Well, 1750 is here. This is greater than, so you can see on your table, 1750 would be somewhere right about here. So we want the probability here and above that. So you can see that that encompasses almost all of the curve. So when we find our probability to be 95%, that isn't that unusual. And so that's kind of what we would expect to find. Make sure that you use the correct standard deviation for this. Part D is just a between problem. Nothing fancy here. It's just like the problem before. You find the probability where you change the initial value and the ending value, or your lower and your upper limits, and you get 42.4276. Now E is different. They actually throw this in real quick. They say, you know, wait a minute, we're going to change the standard deviation on you midstream, and we're not really going to make a big deal of it, but make sure they change this. This is for this particular question only. They change the sample size back to 15. And so we have to divide the 26,250 by 15 and use that value. And so we would use normal CDF of 1750, because when you divide that value, 26,250 divided by 15 gives you 1750. And so that's the question. It says, what's the probability that it costs over that amount for 15 different apartments? And so we're going to find out, well, what would it be like if, or what would the probability be if X was greater than 1750? So the average individual would be paying more than 1750. So you can work this out this way. And it turns out to be just over 90%. Part F changes gears just a little bit. We're talking about the end of the percentile. I drew a picture just to kind of make sure that you remember what the percentile is. The percentile is nothing but the probability or the area under the curve to the left of some number. It's always to the left. It's never the other direction. It says for the individual in letter F. And so we're going to be using the original standard deviation of 150. Because this is asking me for a number, we're going to use inverse norm. Remember, normal CDF gives us the probability, and inverse norm is going to give you the actual values. In this case, I made notation to, this is the individual component. That's what the individual means. I'm going to keep that standard deviation the same. So my result ended up being $1,878.66. So it makes common sense to keep that to 2 decimal places. So anytime that kind of occurs, you feel free to make that necessary adjustment. In part G, it says not just it takes the 70 percentiles to the same. So the picture would be exactly the same as it was in F. But this time, instead of using 150, I'm going to have to adjust my standard deviation back to what we originally found at the beginning, where we had my standard deviation was equal to the 30 up here. Okay, so this is how it would look. Inverse norm again. So it turns out to be 1,815.73, which makes perfect sense when we talked about as the standard deviation, as the sample size goes up. In this case, we went from 1 to 25. The spread shrinks, so that we would expect this number and this number to be different. And this specifically, this one needs to be closer to the mean. and it definitely is. Okay, so that's inverse norm versus normal CDF. Make sure that you remember when I ask you about the individual versus the group or the average, that's what you're going to take care of. Number 2, okay, part H. Okay, this is, it basically asks you a question. If you increase the sample size, what would be the differences in all the different parts? What I wanted you to remember was that with the central limit theorem, there are 3 things you want to talk about: shape, center, and spread. All right, so increasing the sample size would decrease spread. It makes the shape become more normal, and it would leave the mean the same, or it would have no effect on the mean or the center of the distribution. Make sure that anytime I ask you to comment on what the central limit theorem says, those are the 3 things that you want to remember. For number 3, we're going to basically explore the margin of error formula. And on the back page, it really becomes a lot more computational. Really not a whole lot of interpreting. Even straight through the calculator, it's pretty straightforward. So the margin of error formula, if you haven't got this down, is margin of error equals z star times the standard deviation they give you divided by the square root of the sample size. Now that's S, sometimes it's S, sometimes that's sigma. It really doesn't matter what you do in that respect, so they're kind of interchangeable. I'm just going to kind of throw the next couple of questions up. This is how you'd approach this problem. It's really direct. If I've asked you to find the margin of error, you're going to find the z star. Remember, z star is just it's a critical z-score that corresponds to a specific confidence level. You're going to plug all this stuff in, and pretty much you're just going to work it out. So in number 3, we get 0.0814. And number 4 is 0.0277. And in number 5, you got 0.0930. So if you wrote these as percentages, it would be 18.14%. I'm sorry, 8.14% for number 3, 2.77% for number 4, and 9.3% for number 5. Okay, this really is directly right into the formula. Really not a lot of variation on all that. The next part, where we talk about sample size or confidence intervals, that changes a good bit. And so we're going to talk a little bit. You have a couple options for that one. For number 6, it asks us to find the confidence interval for each problem. Now, I've written the confidence interval formula on the board for you. What I want you to walk away from this is that you can manipulate that. In other words, if I gave you the formula, then you know how to plug it all in, and you know what each letter represents. And so if I give you one and leave one away, or if I give all of them and leave one, you can find and you can use the formula. Now, truth is that you're probably not going to use that formula a whole lot. A lot of you, most of you, probably use your calculator. So kind of I'm going to walk you through both steps, both pieces. And so if I just plug it into the calculator, or to the formula, we have 500. This is number 6. 500 plus or minus 2.326. That's the confidence level, or the Z star for 90%, 98%. We use a standard deviation of 1.5 and a sample size of 1,500. If you plug all that in, add it, subtract it, you get 499.91 is your lower limit. Your upper limit is 500.09. Now, that was by hand. In a calculator, just if you can't remember how to get there, it's probably really important to know how to do this. You're going to press Stat, so grab your calculator so you don't have them out. Stat, go to Tests, that's pressing over to the right once, and then you're going to go all the way. In my calculator, I have a TI-84. It's number 7. Okay, the Z interval, it's at the bottom of my screen. If you have a newer color screen one, I don't know that it's the same. But just look for Stat, then go to Tests, go all the way down to Z interval. Be careful, this is not a Z test. If you click Z test, it's going to ask you for some other things that you don't have. So Z interval, And here are the inputs we're going to use. We're going to use stats. You have a choice of data or stats. Pick stats and then input all this information. Right? We have it's the same information that you plugged into the formula. You tell the mean, you tell the standard deviation, you tell the sample size, and you tell it what confidence level would you like to use. The one thing I don't need is the Z star. Because it's in the calculator knows the critical values, and so it just plugs it in for you. Either way, you're going to get the exact same confidence interval for this problem. Okay, here are the rest of those, and I went out and wrote it in the formula. I know that if you use the calculator, there's not a whole lot of work to show, and so I went ahead and wrote it out in the formula just so you can see it. Number 7, you'd be 199.88 to 200.12, 199.83, 200.17 for 8, and 9 is 249.96, 250.04. If you didn't recognize it, but each one of these are symmetric over the mean. And so if you look at the interval here, if I were to take this value and this value and average them, add them together and divide by 2, what is right dead center between those two? You're going to find it's the mean. And that's true for every confidence interval. If I add this interval and this interval, or add these two values, divide by 2, I get that number. Add this plus this, divide by 2, I'm going to get that. All right? So if I ever give you a confidence interval and say, well, here's the interval, what's the mean? Well, the only thing you have to do is add the two endpoints, this part plus this part, divided by 2. And that's going to give you your mean of the distribution. All right? Let's move on to the next one. Number 9, number 2. There are 2 number 9s if you didn't catch that. We're going to be finding sample size. So what I thought would be a useful use of our time would be, let's actually take the margin of error formula that they give us and let's solve it for n so that I kind of have a new formula, which is really based on the old one, that's just n equals, and then I can plug it all in rather than having to plug it in and then solve and go back and forth. Let's just do it one time. So this is what it would look like. I'm going to go ahead, I'm going to divide by this z star, cross multiply, and solve for n, basically what happens. And at the end you square both sides to get rid of the square root. Right? And so you can see that here. If you missed all that, you're like, I have no idea what he just did. This video is available on my website just like you're watching it now, so you can go back and look it over and over and over again if you need to. Okay, it's straightforward basic algebra solving for the variable in question. Okay, take your time and work through that some other time if you need to. So we got this, we got our values right here, we got it all set up. It's going to be the standard deviation times z star divided by the margin of error squared. If you follow those steps in that order exactly, standard deviation times z star, then divide by me, square the values, and that's going to give you your sample size. So let's look at an example. So the first part, we have z star equals 1.645. If you plug it all into the formula, just like it looks, and in my calculator, I literally typed it in 0.45 times 1.645. I hit enter, then I divided by 3, or 0.03, and then I squared the number, and I got these two values. Remember always to round up when you're finding sample size. Number 2, or 10, this one's got a bit of a trick. They threw this part in. If you look at number 10, it doesn't say 0.02 is my margin of error. It says 2%. Be careful. It is common to write the margin of error as a percentage, not as a decimal or proportion. You must remember always change that to a decimal. If you don't, it will be wrong. Okay, you'll get a really, really large sample size. It won't make sense. So don't forget to use the decimal in place of that. Okay, so you get 153,664. Okay, the one thing that is common, I've said this earlier, that's common with finding sample size is the fact that people forget to round up. It does not matter what your decimal point is. if you have an extra leftover part, if we're finding sample size, basically this is related to margin of error. I don't want to have a margin of error less than what I started with. So we always round up. So on to number 11. Okay, this one's pretty much the same as like before. Just plug it in. Remember to round up. Number 12. Let's be smart. That's just the same as number 10. So I hope you didn't do that again. If you did, it's good practice. Just make sure you don't use 2 as the percent. Use 0.02. Number 13. This is one that changes gears one more time, and it says, all right, now we're going to find standard deviation rather than all the other things. And so, just like last time, I thought it would be useful if we took the formula and solved it for S instead of ME. So if we rearrange it, this was a lot easier. So basically, if you divide the margin of error by the Z star and then multiply by the square root of the sample size, you've got standard deviation. So it looks kind of like this. Go to 4 decimal places when you're working with standard deviation. That's kind of just common in statistics. You'll use 4 decimal places pretty much for everything, unless it makes sense. Like if you're working in money, like with dollars and cents, then it makes sense to go to 2, but in this case we're going to keep 4. Number 14 is the same. We're going to use the same formula as before, and I have the difference. So in 13 the answer was 0.5301, and 14 was 1.22434. Those are standard deviations. Okay, I want to leave you with a couple of other questions. So, to conclude, well, first of all, your homework is, of course, to complete the review sheets. If you didn't work these out, I went through this kind of quickly. I wanted to give you some time in class to kind of finish this up or ask questions if you have, or if you need to watch some parts over again, if you need to work with your classmates, make sure that you have this down, because your test is going to be very similar to these worksheets that we did in class. I want to leave you with a couple of extra questions that you can explore. Make sure that you have these answered before you come to class tomorrow. You can talk about them now. So answer the following. Number 1. What happens to the confidence interval when you increase the confidence level? I'll say that one more time. What happens to the confidence interval when you increase the confidence level? Question mark. All right, next question. This one's a little bit more complex. How can I increase my precision with my confidence intervals? In other words, if I'm trying to predict a value, like the question or the example that I always use is, you hear confidence intervals a lot of the time when you hear the weather report. If it says, well, there's a 20% chance of rain, blah blah blah. A lot of this comes from this kinds of statistics. And so here's a confidence interval that is completely accurate, but very, very imprecise. So I'm going to make a prediction that tomorrow's temperature, the high tomorrow, is going to be somewhere between negative 200 and positive 200 degrees. In fact, I'm gonna go out on a limb. I'm gonna say I'm 100% confident that that's going to be accurate, right? So I've got super high confidence in that answer. However, the precision is so crappy that it's completely useless. Everybody knows that the temperature is going to be between that, right? But if I get so incredibly precise, okay, then I also lose my confidence. So I want you to write a statement. What can I do to increase my precision? And I have a choice. I can choose a couple of things when I create a confidence interval. If I'm the person designing my little sample, I get to pick a few things. So in what ways can we increase precision with confidence intervals? I don't want to say too much. I want you to think about it. All right, number 3. This one's a little easier. How can I increase precision
and reduce margin of error at the same time in a confidence interval. In other words, everything that I want to happen happens. If I do anything else besides what I'm asking you for here, I have a choice. I can be very precise, or I can be very confident. It's inversely related, except when I do one thing. If I do this one thing, then I increase my precision, and I can increase my my confidence. Or I'm sorry, not confidence. I can increase my margin. I can reduce my margin of error. I'm going to keep my confidence level the same, but I can increase my precision, and I can be more. I can reduce my margin of error. How can I do the two things I want to do at the same time? There's one thing that I can take into account to make that happen. See if you can figure that out, and we'll talk about it tomorrow. Study for your test. If you have any questions, I'm still available through email, so please send me your emails. I'll try to get back to you as soon as I can. Study up, and I'll see you tomorrow.